Hi, and welcome to the last lesson of this series. This lesson is going to cover everything about tree traversals and operations. Now let's look at tree traversal. It is the process of visiting each node in a tree in a systematic manner. It is essential for many operations like searching, printing, and modifying tree data. Pre-order traversal. You visit the root node first, then recursively visit the left subtree, followed by the right subtree. The steps for pre-order traversal are you visit the current node, recursively traverse the left subtree, then recursively traverse the right subtree. The use case is in expression trees. It is useful for evaluating expressions. Also in cloning a tree, when you need to copy the entire tree structure of a tree. Let's look at this tree, wherein A is the root node of the tree. It has two children B and C. The subtree B has two childs D and E. In case of pre-order, the result is going to be A, B, D, E, and C. Now, let's look at in-order traversal. You visit the left trees first. You visit the left subtree first, then the root node, followed by the right subtree. The steps are to recursively traverse the left subtree, then visit the current node. After that, recursively traverse the right subtree. The use case is binary search trees. It produces sorted order of nodes in a BST. In expression trees, it is used for infix expressions. Let's look at this tree, the same tree from our previous example. A, B, C, D, and E. The in-order traversal is going to be D, B, E, A, and C. Now, let's look at post-order traversal. You recursively visit the left subtree, then the right subtree, and then visit the root node last. The steps are to recursively traverse the left subtree. Once that is done, then you recursively traverse the right subtree. After that, you visit the current node. The use case is in deleting a tree. Post-order ensures all children are deleted before the parent. Because if you delete the parent first, you'll not have access to the other subtree that is there. Also, in expression evaluation, for postfix expressions, it will be evaluated after the operands. Let's look at the example that we have been working on, the tree A, B, C, D, and E. The post order for this tree is going to be D, E, B, C, and A. Let's look at it in action. Let's look at the depth first search and the three parts of it in order, pre-order, and post-order traversals. And the graph we'll do it is on this 1, 2, 3, 4, and 5. So we'll be looking at each of these. To summarize, in order means you traverse the left subtree, then you visit the node, and then the right. Pre-order is that you first visit the root node, then the left, and then the right. In post order, you first visit the left, the right, and then the node. So let's look at the same thing for this. Let me write it here. Let's look at in order. So in case of in order, we're going to go the left subtree first, print out 4, come back up, go to 2. Now that we have reached 2, we go to the right subtree and we print out 5. After this, we come back here. We've already displayed 2. We come back here. We display 1. After we've displayed 1, we go in the subtree. There's nothing here. Then it comes back here. 3. There's nothing here. And that becomes the in-order traversal. Now, Let's continue on to the same example we were looking at for in order to do it for pre-order. In case of pre-order traversal, let me see if I can remove the blue ones. Okay, and I can just reconstruct this. Now, in case of pre-order traversal, we first visit the root node, then the left subtree, and then the right. So we first are here, so we display 1. Then we come down here, we are here, so we display 2. Then we are here, we display 4. Now, the next is that there's nothing here, there's nothing here. So we come back and come here. So we display 5. Nothing here, nothing here. So we come back up, then come back up to 5, then already displayed 3, and there's nothing here, there's nothing here. So this becomes our pre-order traversal. Now, let's look at the post-order traversal. In post-order, we first go to the left, right, and then to the node. So we are first going to the left. There's nothing here, nothing here, so we are at the leftmost part. We print out 4. Then we go to the right of this. We come back here, go to the right. So we come to 5. Come back here, there's no more left or right. We print out 2. Then we come back up. Again, first go towards the right of it, and we find 3. There's no children to 3. We come back to the root and display 1. So this is now the post-order traversal for the given tree. Now, all of these were depth-first search traversals. Let's look at breadth-first traversals, which is also known as level order traversals. In this, you visit the nodes level by level, starting from the root. In this, you visit the nodes level by level. In this, you visit the nodes level by level, starting from the root. And all nodes at a given level are visited before moving on to the next level. The steps are: you start with the root node, enqueue it. Then dequeue a node, visit it, and enqueue the children, that is the left to right, and repeat until this queue is empty. The use case is finding the shortest path. It is used in unweighted graphs and tree search problems. Level order printing. Display tree elements level by level, which is useful for visualization as well. If we look at the same tree example we have been looking at of A, B, C, D, and E, the level order traversal is going to be the first level, second level, and the third. So A, B, C, D, and E. Let's look at this in action. Now let's look at BFS traversal in a tree. Let's consider our tree to be like this. And the tree node connections are like this. In case of BFS, we are going to do a level order search. You see, this is our level 0, level 1, and level 2. So the output is first we look at all the nodes in level 0 and display them out. Now, there's no more nodes in level 1, in level 0. So we go to level 1 that's there. Select the first node. Are there more nodes? Yes. 2. And are there more? 3. Yes. And parallelly, now that we have exhausted everything in this level, we move to the next level. Here, the first element is 4. So we've displayed this. Then 5. Then 6. And then 7. So our BFS traversal for the tree is this. BFS is pretty direct and straightforward. It is breadth first. So level by level, everything in the level comes out before you go in depth of any of the tree levels. Now, let's look at tree operations. The first is insertion. Add a node to the tree while maintaining the tree's properties. In binary search tree, insert the node based on the key values, which is left for smaller and right for larger. In deletion, you need to remove a node while preserving the structure and properties of the tree. In case of BSTs, you need to handle three cases: nodes with no children, one child, and two children. If it is a leaf node, that is a node with no children, you simply remove it. If it is a node with one child, you replace the node with its child. If it is a node with two children, you find the in order successor and replace it with the node being deleted. In search, you find a node with a specific value. In case of BSTs, you start from the root and recursively search left or right based on the key that you are looking for. Now let's look at the complexity of tree traversals and the operations. If we look at the pre-order, in-order, post-order traversals, the time complexity is O of n. The space complexity is O of h, where h is the height of the tree, wherein especially for pre-order traversal, it is O of h for recursion stack. For breadth first traversal, it is O of n time complexity, and the space complexity is also O of n because of the queue storage that we do. For insertion, for BST, in case of BST actually, insertion, deletion, search, all are O of log n, and the space complexity is O of h. A few applications of trees. First is expression evaluation. Pre-order, in-order, and post-order traversals are used to evaluate and convert between different forms of mathematical expressions. In file system navigation, BFS for level order traversals in directories and folders. Decision trees, pre-order and post-order for traversing decision trees in machine learning. Hierarchical data representation, tree operations for querying, inserting, deleting hierarchical data in applications like organizational charts or family trees. Trees have a very widespread application, and different ways of traversing a tree can be useful in achieving different use cases. As we come towards the end of the lesson, let's look at a few key takeaways. The first is tree traversals are fundamental to working with tree structures and see various real-world applications. Pre-order, in-order, and post-order traversals are depth-first methods. They're used for processing nodes in different sequences. Breadth-first traversal algorithms are essential for level order processing and shortest path algorithms. Tree operations like insertion, deletion, and search depend on traversal techniques and tree structure properties. This brings me to an end of this lesson. Take the quiz, test your knowledge, and Thank you.